Okay, we're going to look at mass and weight here, and we've already kind of talked about it because I think the book is doing something in a different order than my brain works, and that's fine because that's why you have a book and a video. So the biggest thing here is that mass is not equal to weight. So whenever, for example, someone says that they weigh, 80 kilograms, that's not actually their weight, that's their mass. Whereas if someone says, well, I weigh, I think that's the equivalent to like 170 pounds, that's a force, which is a weight. So whenever people say, oh, well, I weigh 80 kilos or I weigh 170 pounds, those are actually, from a physicist perspective, two different measurements. Now, does the average person on the street care? No. But in theory, if I go to the moon, that mass is not going to change. Like, if you compressed me into a cube of a specific density, I would take up the same amount of space no matter where I am. It's just that cube might weigh differently if it's on the moon or if it's on Earth or if it's on Mars, if that makes sense. Okay, so that said, from a physics perspective, if we're kind of like TLDR, too long didn't read, just in case we don't have a ton of Redditors out there. If I'm giving you something in pounds, it's a force. If you need it to be a mass, you have to divide it by the speed of gravity on Earth, because we're assuming all of our problems are going to be here on Earth, because you have pounds divided by 32.2 feet per second squared, and that's going to get you, I don't know, 170 divided by 32.2, that's a times, divided by, and that's going to give you 5.28 slugs is how they measure it in customary imperial units. If I, for example, need, or I'm given the kilograms and I need it to be a force, it's kilograms times 9.81 meters per second squared. And so then that turns out to be 80 times 9.81. And so that's 784.8 newtons, so 785 newtons. Okay, so these here are both mass. So I could say that the mass is either 80 kilograms or 5.28 slugs. If I got that conversion right, I think it's close enough for what we're trying to explain here. And then for the force, I would say it's either 785 newtons or 170 pounds. And this is important, right, because we have that equation, sum of the forces equals mass times acceleration. The force goes here, and then the mass would go, those look the same. I was trying to get a different one. And then the mass would go here. Okay, does that make sense? So on one side of the equation you use force, on the other side of the equation you use mass, but to get them to match the same units, you're going to multiply mass times the actual acceleration of the object that it's actually experiencing. Like, it's kind of like it doesn't matter. Let me just leave it at that before I confuse things. Force, if you're switching between, customary imperial units and SI units, you're just going to have to pay attention to what's going on. It's pretty common early on for students to make mistakes like forgetting to multiply by 9.81 or dividing by 9.81 or multiplying by 32.2 because their brains are just not quite remembering everything straight. So hopefully just a quick reminder of how these are different. So this is your weight, and this is where it says weight is mass times acceleration. I also refuse to accept 9.80 because with 3 sig figs, it's 9.81. So I legitimately have no idea what's going on here. I'm super sad about it, but for the purposes of, if you're ever in my class and I ask you what is G, it's 9.81. But, I mean, if you're in like a clapping for physics class, like for physics for, non-majors who just kind of want to take a physics class, I think they use gravity as 10, okay? So does it really matter? No, but I am choosing to, you know, put my foot down about this. Anything else here that we want to talk about? This is just another math question. A farmer is lifting some heavy rocks, moderately heavy rocks. He lifts a stone that weighs 40 pounds, about 180 newtons. So maybe I was close. Because what did I say? Oh, who knows? Okay, so what is the mass, or what is the acceleration? So let's actually solve it in both units, just for funsies. So here's our, what do you call that thing? We're going to draw a free body diagram of the rock. He's being pulled down with a weight of 40, and he's pulled up with an unknown force, and he's got a unknown motion this way. So AY is non-zero. Okay. So AY, I don't know why I did that. I need to do that. AY is non-zero, and it's going up. Okay, positive. So if I do the sum of the forces in the y direction, I've got force goes up, weight goes down, and that equals mass of the rock times acceleration in the y direction. Okay, so force goes up, I don't know what that is, weight is 40. Now the mass, so this is 40 pounds, so that means the mass is 40 divided by 32.2 AY. Oh, and it tells me what the AY is, it's 1.5. Oh, we'll see. I was like, wait, I'm missing something. 1.5, but that's meters per second. Dang it. Okay, so let's try this again. I've got to pay attention to my units. So this is in pounds, this is in pounds, this is in feet per second squared. So I can't just multiply it by 1.5 meters per second. I've got to convert that. 1.5 meters per second squared. I need to convert that to feet per second squared. And I can never remember meters to feet, but I can remember meters to centimeters. Centimeters is 1 meter. Dang it, that's upside down. Let's see, 1 meter is 100 centimeters, and I know that a 2.54 centimeters is 1 inch. Okay, I really should learn this. And 12 inches is 1 foot. So then the meters will cancel, the centimeters will cancel, the inches will cancel, feet per second squared. Okay, so I've got 1.5 times 100 divided by 2.54 times 12. What is that number? Just because I'm probably going to look at it and go, oh yeah, it's that number. 3.28? Nope, not going to just know that number. Do I know the inverse of that number? Probably not. Oh, 3048. Yes, that's the number I recognize. But I'm never going to remember it, or I'm going to get the 3 and the O and the 4 all in the wrong place. So anyway, the final answer is it's 4.9 feet per second squared. 4.9 feet per second squared. So 4.9, and this is feet per second squared. So since that's on the top, technically it's up on the top, so these will cancel out, and I'll have pounds on one side and pounds on the other side. Okay. Wow, this actually ended up being more interesting than I thought. So I have F equals 40 divided by 32.2 times that 4.9 thingy. Notice I'm using the whole number, not the rounded off number, and then I'm going to add 40. So it's 46.1, 6.1, and I'm in the unit pounds. Okay, well that was fun. Now let's do it in the other units. Okay, so now the weight is, I already forgot. The weight is about 180 newtons. So I'm still doing the sum of the forces in the y. The weight is going down, the force is going up, and that equals the mass times acceleration in the y direction. Okay, so the weight is negative 180 newtons plus the force equals mass. See, this is upsetting to me, because what I wish it had done is given you something like this. Like, let's pretend that weighs 40 pounds or is 18.3 kilograms. Okay? Let's pretend it did that, because that's what would make sense to me. If I was writing a problem, I would make the problem like that to make sure you knew what you were doing. Okay, so we're just going to pretend that's what the problem is said. Okay, so if it says that the stone is 18.3 kilograms, now what you need to do is you need to make sure that all the units match again. Okay, so the weight is not just the 18.3, but it's 18.3 times 9.81, because this is in kilograms. Here, I'll change the color for that. This is in kilograms, and this is in meters per second squared. And when I multiply those together, I get newtons. Then plus a force that's unknown. Now the mass of that object is 18.3 kilograms. And then the acceleration is 1 point, maybe this guy over a little bit more. The acceleration of that guy is the 1.5. I don't have to convert it this time because it's in the right units. Do you see why my problem is better? Did you know sometimes you get what you pay for? Well, and this is a free video too, so you're getting what you pay for there too. Okay, so this means that this is in newtons and this is in newtons. So see how my units match? Okay, so if you're getting confused, always go back to the units. So if it helps, I've got negative 18.3 times 9.81. Shockingly, it's going to be 180. So I have negative 180 newtons plus F equals 180 times 1.5. So that's 27.5 newtons. And you see how it's both newtons, and so I can add newtons to newtons or apples to apples. So the force, and this is where I'm going to mess something up, is 27.5 plus 180. And that's going to give me 207 newtons. Okay, so those numbers are not at all the same, but they're comparable. So engineering, you'll see words like pound mass and pound force, and I'm not getting into any of that right now. Okay, I'm just letting you know those are words that exist. Pretend you don't know that. Or if you do know, what I'm saying is, if you do know that, we're not getting into this. For the purposes of this class, pound is always a force. Okay, did they get 207? Probably. Yeah, 207. Okay. So hopefully that is a good start on that, or a good clarification. And then we'll go ahead and we'll go into Newton's third law here.